Every server on Earth disappears. Every router goes dark. Every undersea cable, every data center, every satellite uplink, gone. No Google, no streaming, no banking, no GPS, no cloud. The entire digital nervous system of civilization vanishes in an instant, and all that's left in your hand is one copper wire. The question isn't whether you could rebuild the internet. The question is how many separate, brilliant inventions stand between that wire and a working global network. The answer is hundreds. And the story of those inventions is one of the most astonishing chains of human ingenuity ever assembled. Start at the beginning. For almost all of recorded history, information traveled at the speed of a horse. A message sent from Rome to London in the year 1200 took weeks to arrive, assuming the rider didn't die in a ditch. That was the hard ceiling on human communication for millennia. Then, in 1837, two inventors changed that ceiling permanently. Samuel Morse in America and Charles Wheatstone in Britain independently demonstrated that electrical pulses could be sent through a copper wire to transmit coded signals over long distances. The telegraph was born. By 1866, a copper cable roughly 4,800 kilometers long had been laid across the floor of the Atlantic Ocean. A message that once took 10 days by ship now crossed between continents in minutes. Morse code turned the wire into a language. Dots and dashes, short pulses and long pulses, each combination mapped to a letter of the alphabet. The copper wire had become a communication channel. But dots and dashes can only carry so much. The next leap was voice. In 1876, Alexander Graham Bell transmitted the first intelligible spoken words through an electrical wire. The telephone turned the copper line into something far more intimate and far more scalable. Within decades, telephone exchanges began appearing in every major city on Earth. Operators sat at enormous switchboards, physically connecting one caller's line to another by plugging cables into the right sockets. By the early 20th century, automatic switching systems replaced the human operators, and the telephone network became a vast self-rotating machine. At its peak, the public switch telephone network connected hundreds of millions of people across every continent. It was the largest machine humanity had ever built up to that point, and it was built on copper wire. But voice was still just one narrow stream of information. To carry something more complex, humanity needed a completely different kind of machine. Before computers could talk to each other, humans had to invent computers. In the 1940s, the first electronic computers ran on vacuum tubes, fragile glass cylinders that controlled electrical signals by heating a metal filament inside a vacuum. The ENIAC, completed in 1945, used roughly 18,000 vacuum tubes, weighed 30 tons, and occupied an entire room at the University of Pennsylvania. It could perform about 5,000 calculations per second, which sounds impressive until you realize a modern smartphone chip does roughly 15 billion per second. The vacuum tube was the right idea wrapped in the wrong package. Then, in 1947, three physicists at Bell Labs, William Shockley, John Bardeen, and Walter Brattain, demonstrated the transistor. A transistor does what a vacuum tube does. It amplifies and switches electrical signals, but it does it in a sliver of semiconductor material rather than a glass bulb. By the 1960s, engineers learned to etch thousands of transistors onto a single thin chip of silicon. Gordon Moore, co-founder of Intel, observed in 1965 that the number of transistors on a chip was doubling roughly every 2 years, a pattern that held for decades. By the 1970s, a single silicon chip could contain the processing power that once required a room-sized machine. The computer had become small enough to actually use. Now came the hard part. Two computers sitting in the same room could share a cable and exchange data. But what happens when thousands of separate computers, running different software at different universities, need to share information across the country? The first instinct was to connect them the way telephones were connected. Dedicate a physical line between every pair of machines. This is catastrophically inefficient. In the 1960s, a Rand Corporation researcher named Paul Baron proposed something different. Instead of sending data as one continuous stream along a dedicated line, break it into small, individually addressed chunks called packets. Each packet travels independently through whatever path happens to be open. When all the packets arrive at the destination, they are reassembled in the correct order. This idea, called packet switching, was developed simultaneously and independently by Donald Davies at Britain's National Physical Laboratory. It meant the network had no single point of failure. In 1969, the United States Department of Defense funded the first real test of this idea. A network called ARPIT linked 4 computers at the University of California, Los Angeles, the Stanford Research Institute, the University of California, Santa Barbara, and the University of Utah. On October 29, 1969, operators at UCLA attempted to send the word login to Stanford. The system crashed after the letters L and O. The first message ever transmitted on the proto-internet was low. By 1972, ARPANET had grown to 37 nodes. Researchers discovered they could send not just data files but also electronic messages between users. Email was invented almost as an afterthought, but ARPANET was still one closed network with one set of rules. The world had dozens of other networks, all speaking different technical dialects. None of them could talk to each other. To solve that, 2 computer scientists, Vint Cerf and Bob Kahn, developed a pair of protocols published in 1974. TCP, the Transmission Control Protocol, managed the reliable delivery and reassembly of packets. IP, the Internet Protocol, handled the addressing, giving every device a unique numerical identity so packets could find their destination across any network. Together, TCP/IP created a universal language every network could speak. The Internet, by strict definition, is not a thing. It's a set of agreements, a promise that any device anywhere speaking TCP/IP can reach any other device speaking the same rules. Routers, the physical machines that read IP addresses and decide where to send each packet, became the traffic directors of this global system. As more networks adopted TCP/IP through the 1980s, the original copper telephone lines struggled to keep up. Voice calls needed relatively narrow streams of data. Digital networks needed something with far more capacity. The answer was fiber optics, cables that carry not electrical pulses but pulses of light through strands of ultra-pure glass. A single modern fiber optic cable can carry more than 100 terabits of data per second. Compared to copper, fiber made the network's arteries effectively limitless. By 1991, a British computer scientist at CI named Tim Berners-Lee had added one more layer on top of TCP/IP. He invented a system for organizing information as interconnected documents, each with a unique address, navigable through a simple piece of software called a browser. He called the protocol HTTP and the system the World Wide Web. Most people still confuse the web with the Internet itself. The Internet is the infrastructure, the global network of cables, routers, and protocols. The web is one application running on top of that infrastructure, the way a phone call is one application running on top of the telephone network. Within 3 years of the web's public release, the number of websites had grown from 1 to over 1 million. Search engines appeared to navigate the flood. Then broadband, then streaming video, then smartphones, then social media, then cloud computing, then artificial intelligence running on data centers the size of small towns. Today, the Internet is physically sustained by roughly 440 active undersea cables stretching over 1.3 million kilometers across the ocean floor. About 5 trillion gigabytes of data flow across the global network every single day. Roughly 5 billion people log in. Tens of billions of devices from thermostats to satellites speak TCP/IP. The whole astonishing structure. Every search, every video, every payment, every message traces back through a chain of inventions to a single, simple insight from the 19th century. Electricity flows through metal. If you control that flow precisely enough, you can encode meaning. And if you can encode meaning, you can send it anywhere. Everything after that, the transistor, the packet, the protocol, the fiber, the web, was just humanity getting better and better at the same trick. One copper wire, centuries of ingenuity, and the largest machine ever built.